Hi everyone, I'm Julia Zhang. I'm going to introduce a project that we're working on at Ohio State. We're trying to apply machine learning techniques to the control of power electronics, and we hope to have improved lifetime for wide bandgap power devices. And the devices that we're using in this project are 3.3 kV silicon carbide MOSFETs. Usually, high current rating power modules will have a few chips in parallel. We hope all the chips will have the same current flowing through them, but in real world applications, the current may not be the same for all parallel chips. We list a few factors that may contribute to this. For example, the electrical characteristics of individual chips might not be exactly the same. The circuits for individual chips may not be exactly the same. Here we show some thermal simulation results of our power module. The heat dissipation for those chips is not uniform, so you can see the temperature difference. Over time, some chips will age faster than the others. And what we're trying to do in this project is to find a way to achieve even current sharing between parallel chips or have even thermal stress for them. By doing this, we hope to increase the lifetime of the power module. If we want to control the current in parallel chips, we will need to have separate gate drive circuits for individual chips. Now talk about what features we need for the gate drive circuits first. Now talk about how we plan to apply machine learning algorithms to our study. In the gate drive design, we added a function to have a few different turn-on resistance values. So for example, this design here has 4 different turn-on resistance values. We also added a function to measure the gate leakage current. The switch inside the green box is normally on. It will bypass this 50 ohm resistor. It's a high accuracy resistor. After the switching transient, we will turn off the switch and then we can read the voltage across this 50 ohm resistor, which will give us the information of gate leakage current. Other than using various values for the turn-on resistance, we also have an adjustable gate drive output voltage that varies from 15 volts to 25 volts, and we can control this digital potentiometer online to adjust the voltage output. This is the half-bridge module we're designing. Each of the top switch and bottom switch has 3 chips in parallel. These are 3.3 kV silicon carbide MOSFET devices, and we integrated shunt resistors into the power module to measure the current flowing through individual chips. These are the decoupling capacitors, and we integrate them into the power module to help reduce the power loop inductance. Then I'll talk about how we plan to implement machine learning algorithms. So first, artificial intelligence has the biggest scope. Machine learning is a subset of artificial intelligence. And under machine learning, we have 3 big categories: supervised learning, unsupervised learning, and reinforcement learning. And we plan to use classification, which is a type of supervised learning algorithm, to recognize the type of device degradation. And the second, we're going to use regression, which is also a type of supervised learning algorithm, to estimate the remaining useful life of individual chips. And last, we plan to use reinforcement learning algorithms for device control, so we can have balanced remaining useful life for individual chips. And I'll go through the details for each of the 3. Handwriting recognition is a very classic example of the classification algorithm. So during the offline training process, the machine will read a lot of handwritten numbers first. Those are images, and then the machine will scan every pixel of the images, And all the pixel values will be used to train the parameters of a sigmoid function. So basically, the sigmoid function will relate the pattern of the image to the probability of this image being a certain value. So after the training is done, and you can give the machine a random number. For example, the image with number 7 on it, and it'll tell you the probability of this image being 7 is 90% or 95%. Anyway, it's a very high probability number. And the probability of this image being other numbers is extremely low. Then we plan to use the classification algorithm to recognize the type of device degradation. So we know when a device is aging, some of its parameters or electrical characteristics will change over time. And during the offline training, we're going to run a lot of aging tests and collect a lot of data during the tests, like those in the table. And then we can use this data to train the algorithm so it can relate the data pattern with a certain type of degradation very accurately using the offline data. For example, gate oxide degradation and stacking faults. Once the features of different types of degradation are well trained and recognized, the machine will be able to classify what type of degradation the device is experiencing using online data automatically without any input from human. Let's take a look at a simple example of regression, which is a type of supervised learning algorithm. Then I'll explain how we're going to apply it to this project. This example shows many houses and their features. Features like square footage, number of bedrooms, and you can also add more features like the number of bathrooms. And we also know the sales price of each house. So basically, the regression will come up with a hypothesis function for the house price, a function of all the house features, and all the data will be used to train those theta values, theta parameters in the hypothesis function. And our training goal is to find a set of theta values so we can minimize the difference between the sales prices of those houses and the house price calculated using the hypothesis function. And once we have a well-trained algorithm, now we can use this algorithm to predict the sales prices of future houses on the market. In the aging tests, we would have a big set of data with the information like VDS, IDS, temperature, threshold voltage, gate leakage current. And some information like VDS, IDS, temperature can be directly measured. Some information like threshold voltage, RDS on cannot be directly measured online, but those parameters are actually more likely to represent the device health status. With the data we collect in the aging tests, we can apply the regression algorithm to train a hypothesis function. And we need this hypothesis function to map things like VDS, IDS, and temperature to device threshold voltage, RDS on, based on the offline data. And then we can use this well-trained hypothesis function to do online estimation of device parameters like threshold voltage, RDS on, parasitic capacitances, and then we can use those parameters that we got online to calculate remaining useful life for devices. Last, a simple example to explain Q-learning. It's a type of reinforcement learning. The robot's goal here is to get out of the house from one room from any room as a starting point using the minimum steps. So basically during the training, the robot is taking random actions to go from one room to another, just try around. When the training is finished, we will have a Q table like this with different reward values. The Q table will basically tell the robot what to do in the future. And so to tell the robot to take an action with the highest reward value, in this case, and it'll get out of the house in the quickest way. We're going to apply reinforcement learning for the remaining useful life balancing control. So during the training process, we're going to try random combinations of a gate voltage and a gate resistance and observe the remaining useful life changing. At the end, the training process will create a reward table to tell us what combination of gate voltage and gate resistance will give us balanced remaining useful life for the parallel chips. Sorry, it's a short presentation and we're not able to cover a lot of details, but we hope to share more details in future publications. Thanks everyone for your time.